minutes.
Yeah.
Okay.
Okay.
Yeah.
Very good morning, everyone, and in fact, good afternoon to Dr. Koji Wada, who is ahead of
Yeah.
Indian Standard Time. I welcome you all for the Earth and Planetary Sciences Introductory Lecture Series, organized by the Manipal Center of Natural Sciences, a center of excellence under the Manipal Academy of Higher Education. The concept of interdisciplinary research has gained a significant traction, particularly in the last few decades. And we are no exception to this. But how often do we come across such courses being offered in universities or research centers? So, as far as I know, there are very few places which are offering courses like Earth and Planetary Sciences or Paleontology, which always involves collaboration from different fields of sciences or different branches of sciences. So, in this order, when we talk about the interdisciplinary research, we cannot ask for a better place other than the Manipal Center for Natural Sciences, where we have a excellent faculty strength working across different fields of science, ranging from astrophysics, cosmology, planetary sciences, geology, biological sciences, and chemistry. So we thought this is one of the best platforms for the students to start or begin their interdisciplinary research in India. So as a part of this project, we initially wanted to start with an introductory lecture series, mainly to motivate students, young students in particular, and to take up research on this particular field, Earth and Planetary Sciences, which involves the study of the origin and evolution of Earth, but not limited to that, particularly with the advancement in science and technology in the recent times. For example, the remote sensing technology, we got to know the dynamics, the spatio-temporal dynamics of various processes that is happening in the Earth. So having all these advantage with our side, we are organizing this introductory lecture series starting from today, and this marks the today's lecture on space impact experiment in Hayabusa2 marks the beginning of this lecture series, and we have with us today Dr. Koji Wada, Planetary Exploration Research Center, Chiba Institute of Technology, Japan. And thank you so much, sir, for accepting our invite and be here with us today. So I request all the participants, particularly students who are attending offline and online, to make the best use of this opportunity to learn more about this. Thank you. So with this, I invite Dr. Shalima to introduce the speaker to you all.
Thank you, Dr. Vivek. It gives me immense pleasure to introduce today's speaker, Dr. Koji Wada, who is a Principal Staff Scientist at Planetary Exploration Research Center, Chiba Institute of Technology, Japan. So he has done his bachelor's and master's in Earth and Planetary Physics from the Department of Earth and Planetary Physics, University of Tokyo. Later on, he did his PhD in Earth and Planetary Sciences, University of Tokyo. Then after working at the Institute of Low Temperature Science, Hokkaido University, he joined Planetary Exploration Research Center, or PERC, at Chiba Institute of Technology in 2009. So his specialization is planetary science, especially celestial impact phenomena, and he has been working on elucidating various collision phenomena from dust collisions to planetary crater formation by making full use of numerical simulations. As a result, he has participated in the Hayabusa2 project as the sub-PI of the Small Carry-on Impactor, or SCI. He is also a sub-PI of the Deployable Camera 3, DCAM3, which is a device to image the SCI impact. And currently, he is participating in various planetary exploration projects, including Hayabusa2, then the Martian Moons Exploration, and Destiny Plus missions. So I would like to highlight that these are all missions that aim to answer the fundamental questions about how the solar system formed and how life emerged. Okay, so now I would like to invite Dr. Koji Wada to present his talk titled A Space Impact Experiment in Hayabusa2. So over to you, Koji.
Okay, thank you so much for introducing me and inviting me to this great lecture series. Okay, and I'd like to talk about the space impact experiment that was conducted in Hayabusa2 on the real asteroid in space. So let me start. Okay. So introduced by Shalima, thank you. I'm born in Japan and I'm 48 years old. And my major field is celestial body impact and planetary exploration. And I'm very interested in the impact phenomena because the impact makes planetary system. For example, the right figure shows the surface of the moon. There are lots of craters made by impact of the asteroid or something. And the right illustration shows the giant impact that makes that would be believed to make a moon, Earth's moon. So in the various stage of the planetary system formation, the impact played a very important role to make a planetary system. Okay, and now I'm dedicated to the impact exploration. That is an active exploration method to investigate the state of the asteroid, celestial body by colliding something, something artificial with it. And there are a lot of, it's not so lot, but some mission using the impact exploration. The first mission was the deep impact led by NASA. And in this mission impact on comet, and it is very successful. It was very successful, and revealing the content of the asteroid. Comet. And the other one is the L-Cross mission, also led by NASA. And in this mission, impacting impactor onto the lunar South Pole region. And this mission found that there are ice underground of the moon. And recently, maybe some of you already know that mission, and in this September, impacting on the Dimorphos, the secondary of the Didymos asteroid, Didymos, and get a very beautiful and exciting images like this. And then Hayabusa2, I'm talking about Hayabusa2 mission from here. And the Hayabusa2 was very, very successful. And in this mission, impact exploration was also conducted and succeeded. So first of all, I show you the overview of movie of Hayabusa2. But this is made by JAXA, but made before arrival. So this is a imaging of the asteroid, and the target asteroid is Ryugu. And in this mission, as you see, the target marker, a ball, was thrown to the surface, and this is the target of the touchdown. And then the Hayabusa2 touched down to the asteroid and getting a sample. And then above the surface of the asteroid, about 500-meter altitude, the Hayabusa2 released the SCI, the impactor. And then the Hayabusa2 itself evacuate and escaped and behind the asteroid. Why it is necessary to escape? Because and the impactor is exploded, and to shoot the projectile onto the surface of the asteroid to make an artificial crater like this. And then the Hayabusa2 again going to the crater, from the crater in or around the crater to get the samples of interior of the asteroid. And the Hayabusa2 is getting back to the Earth. And that is an overview of the Hayabusa2 mission. Okay. So the mission objective of Hayabusa2 is simply summarized like this. This mission explored a C-type asteroid, Ryugu, and returned to the Earth, collecting Ryugu's samples. So this is a sample return mission. And the scientific objective is to get key data for revealing the origin and evolution of the solar system and life. And on the other hand, this mission has an engineering object. So that is to keep and develop the technology for round trip, go and back, navigation and sampling in deep space. So the target of the Hayabusa2 is an asteroid. And why we focus on the asteroid? So the asteroids are distributed mainly between Mars and Jupiter, that is orbit, that we call asteroid belt, like this. And the asteroid discovered so far is over 1 million, 6.25 million. So lots of asteroids. But some of asteroids orbiting the near the Earth, near Earth asteroids are there. And near Earth asteroid, number of near Earth asteroids, NEA, is around 30,000. So this is also quite large, but compared to all the asteroids, this is a very, very rare asteroid. And why we focus on asteroid? The catchphrase is that the smaller the better, because the small asteroids and their parent bodies are thought or are believed to be relatively cheap information at the early stage of the solar system evolution. So that means the thermal alteration is maintained very low level and not highly pressured. So in asteroid, there are lots of materials not so altered from the origin, the early stage of the solar system. So this is a kind of a treasure of the asteroid or fossil of the solar system. Okay, sorry. So the mission flow is summarized like this. The Hayabusa2 launched on 3 December 2014, and this arrived at asteroid June 27, 2018. So 3.5 years. It took 3.5 years. So long mission, it takes so long because the Hayabusa2's main engine is the ion engine. The power is very, very low, but the cost performance is very high. So the power is very weak, that because it takes a long time to arrive at asteroid Ryugu. And okay, so after arriving at asteroid Ryugu, Hayabusa2 examined the asteroid by remote sensing and determined the area of the first touchdown site. And the first touchdown was conducted on February 22, 2019, and that is successful. And the artificial crater was formed on April 5, 2019 with the impactor as shown in the movie. And then the second touchdown was also conducted and succeeded on July 11, 2019. And departing asteroid and comes back to the Earth and December 6, 2020. And now we have a sample of the Ryugu, and analysis is going. So here I'll show you, I introduce the asteroid Ryugu. What is asteroid Ryugu? The target asteroid Ryugu was previously called 1999 JU3, the simple code name. But this is a C-type asteroid. That means few organic materials is expected on the asteroid. And this is a near-Earth asteroid and predicted to be round shape like this. And around its diameter is around 900 meters. Okay, but arriving at the asteroid, and we saw a surprise shape of the Ryugu. Ryugu is found to be a spinning top-shaped asteroid. top shape is like this. Yes, like a spinning, yeah, form. Yeah, we in Japanese, this shape is very familiar with the Soroban, old type of the calculator. So anyway, this top shape is very surprised because nobody expected this shape, because yeah, top shaped asteroid means generally means it is rotating very fast. But now the Ryugu, the rotating period is only 7 hours and a half, like this. So yeah, compared to the Earth, the period 24 hours, it is very fast. But this Ryugu is very small, and but it is very fast rotating. So but surprised. So this suggested that in the past this was rotating very rapidly, and we found that at the ground there are large craters like this. You can see this is the biggest craters on the Earth, crater cavity on the Earth, on the asteroid Ryugu. So this shows the evidence of the terrestrial body impacts making craters on the asteroid. So I'm sub PI of the impactor, and has a responsibility to make a craters on the Earth. So looking at this crater, I'm a little bit satisfied that we can make craters. Yeah, approaching to the asteroid Ryugu, we saw lots of boulders, rocks, and the Ryugu surface is found to be rich in rocks and boulders. And zooming up, approaching, yeah, Ryugu is rich in rocks and boulders. Yeah, it looks some species looks very smooth, but approaching and close-up view shows that Ryugu is yet rich in rocks and boulders. This is an image from an altitude of 1 kilometer. Yeah, lots of boulders with a size of about 10 meters. And then the closer and closer view shows lots of boulders and pebbles or rocks, and we cannot see no sand on the asteroid. So that was very surprised and shocked for the members of the project, because Hayabusa2 is a sample return mission, and to get sample, Hayabusa2 needs to touch down safely on the asteroid. So for that touchdown, it is necessary that very smooth safety surface is needed. But looking at glance, the surface of the asteroid, there is no such a smooth surface, and safety area was found. Yeah, at first. And Hayabusa2 has a lot of robots working on the surface of the asteroid. One is a Minerva-1, and this is a robot onto the asteroid, and thrown down to the asteroid surface, and the robot jumping to move on the next area and taking a picture. like this. So there are lots of rocks. And another robot was mascot. This is made by the Kunes and DR, the Deutsch and French rover. And also this mascot took a picture the rocks, so we can see any sun on the surface. So the first impression is lock. There are lots of lock, and the question is, and so the small craters, number of small craters are very small. We can see small craters. Yeah, we see the big craters, but the small craters are not. Why? There are mainly two hypotheses. One is it is impossible to form small craters because the surface rich in rock prevent small craters created. Or small craters can be formed, but erased soon. So by the impact vibration or embedded by the ejected deposit, the materials from larger craters, or there are mass movement of the levels. So this is a question of the asteroid on the surface of the Ryugu. And another very surprised point is the surface of the asteroid Ryugu was very dark, and the albedo is only 4% or not, something. But we can see patches of bright spots. So if peel the surface and peep into the interior of the asteroid, we can see fresh and bright or white samples, the materials of the asteroid. So then let's do impact experiment. Why? To answer the following question, it is possible to form impact craters on the surface of Ryugu, or is there the subsurface material fresh on the true materials of Ryugu? To answer these questions, impact may be a very effective tool, because the impacting means making a hole, cavity, digging a hole and open the window to the interior of the asteroid. And to confirm the impact craters, if the impact craters are formed or not, yes, the most impact experiment is the good measure to confirm if the impact craters can be formed or not. And we have a big, not so big, but small impactor, but another impact experiments can be is possible. That is sampling at touchdown. So at the sampling of the Ryugu's material, we shot a projectile of 5 gram tantalum at 300 meters per second. This is small but impact experiment. So and at this impact, the fragments were floated and caught in the capsule. So by such measure, we get samples. Okay, And but this is an impact experiment. So before the main impact experiment, this impact experiment is expected to show the small craters would form, and we could confirm the craters can be formed or not. So I was very excited to see the first touchdown. And first touchdown was conducted, February 22, 2019, and there was succeeded like this. And this is a picture movie of the edge of the sampler home. So going and touch down. Only 1 second. The Hayabusa2 going up. But at that moment, the projectile was fired, and as a result, the most lot of fragments are thrown away, and maybe the some of the fragments caught in the sample. So we got project Ryugu samples like this. But yeah, the touchdown itself was succeeded, but we didn't see the crater clearly. So yeah, we can see maybe a trace of the impact, because the region around the touchdown point became darker. So the interior material will be darker. So we can see the impact point, impact marks, but we cannot see the crater. So yeah, it turned out we should do the main impact experiment with a small carry-on impactor we call SCI. This is the first impact experiment on a real asteroid in the universe. Okay, and the key number is 2 kilograms and 2 kilometers per second. Okay, let me explain the SCI. The role of SCI is very simple. First, I'm a scientist, very interested in the impact science. So I'm very interested in the contribution of the impact science, and concretely, how to make impact craters will be reviewed by this impact experiment like this. And another role of SCI is the contribution to exposure and sampling interior material. That means how is the interior of the Ryugu. So this is a major role of the SCI. So the SCI is actually a 2 kilogram copper projectile shooting impacts to a C-class asteroid Ryugu at 2 kilometers per second to make a crater, and the SCI is equipped on the base of the Hayabusa2, and this is a cross section of the SCI, Small Carry-on Impactor. You can see the most of the SCI is filled with explosive, very dangerous. and this is a kind of technology called explosive formed projectile. So this figure shows how the projectile was impacted, accelerated. Here the base at the base of the SCI, a copper disc of around 30 centimeter diameter is put. Yeah, and then the explosion occurred. Then the copper disc is accelerated by explosion and formed into a hollow hemisphere shape of about diameter of 30 centimeter. Yeah, so you can see this is the time after the explosion. So less than 1 minute, or less than 1 millisecond. Yes, the projectile was formed and accelerated to 2 kilometers per second. Okay. This is very dangerous, but this is very effective tool for impact. And I'll show you the field test of the SCI conducted at Kamioka, Japan. And the SCI is put on the ignition point and targeting the mound far from the ignition point 100 meters. And we can see the explosion SCI, and so lots of fire. Yeah, and that was very, very dangerous. And this images show the movie taken at this camera. So we can we confirm that the very beautiful rounded shape of the projectile. Okay. And at the images taking the mount, so the SCI shoot the center of the circle, the target, and making a crater and throwing away the materials. We call it eject. And this is my favorite movie. And this movie taken by a cam video camera set very close to the target mount. Here. Oh, sorry, here. And yes, you can see the materials thrown away. And yes, I was very surprised at the time, for the first time. At the time, first I saw. Yes, and okay, once again. So you can see a very clear shape of the materials forming like a curtain. So we call the such kind of materials thrown away from the ground ejecta curtain. Yeah. So at the real operation of the SCI, we will get such kind of ejecta curtain, and craters, artificial craters will be formed. And the predicted crater size is very various. So I was afraid, could we find the formed craters on the real asteroid? So from the 10 meters, over 10 meters, or smallest one could be just only 30 centimeters. So I was very afraid, but finally, we get 10-meter size craters. So I was very happy. Okay, there are a lot of problems on SCI operation, and it's described like here. Bringing a big explosive is also itself very dangerous, and impact aiming point is not sure. We don't know the property of the impact point, and the most important, the most problematic point is that we cannot observe the moment of impact from the model C because, as shown in the movie first, this lecture, the Hayabusa2 itself hide away and behind the asteroid. So at the moment of impact, we can see the moment from Hayabusa2 itself. So, but the moment of impact is very, very important for the science. So, how can we observe the moment? That is a very important problem. So, to review, to resolve the problem, we made a deployable camera called the DCAM3 to watch the moment. And DCAM3 is a palm-sized camera system like this, and this has two camera system and antennas, two antennas, and in this very small camera, the batteries, there are batteries and some mechanics, the electronics, and then this is a SCI operation with the DCAM3 separation. Yeah, the SCI is separated around here. This is a Ryugu above the about 500 meters, and then the SCI getting go and behind the Ryugus. This is a safe zone. And in the middle way of the escape, the DCAM3 was separated here at the best position to see the impact. Okay. And this is the movie made by the NHK, the Japanese TV, national TV broadcast. And yeah, this DCAM3 was separated and waiting for the moment of the impact, like this. And at the timing of the impact, we will observe the beautiful ejecta current. This is an expectation. So, what's the result of the actual SCI impact? Okay, on the blocky log surface rich in boulders. Okay, the aiming point is like this, and around here, and the precision of the shooting is very bad. So the pointing, aiming this point, but the SCI is possible to impact within this big region. But as a result, the projectile impacted very close to the aiming point. Okay. And these are images of SCI separated from the Hayabusa2. Yeah, this SCI is separated very as planned. And then DCAM3 was alive. Yeah, I am here in the operation room, and these are the members of the DCAM3, and we are very happy DCAM3 was alive, and yeah, sending the images like this. Yeah, you can see something thrown away. So this is a ejecta current made by the impact of the SCI. So this is the growth of the ejecta curtain taken by DCAM3 and time-lapse images movie of the ejecta curtain growth. Yeah, this is a very, very good and my favorite movie in the world. Okay. And this actually observed more than 500 seconds. Very, very slow process because the Ryugu has a very small gravity. Only the 10 to the minus 5 G. Yeah. Very low gravity makes the process very slow. Okay. And finally, we found that the more than 10-meter size crater was formed. And this is the same size as craters formed on the sun field, even though a border-rich field. Yeah. Before the SCI crater, SCI operation, we predicted that in such a border-rich field, only small craters should have formed. But actually, we got very good, very large size craters. So this indicates that small craters are possible to be formed on small asteroids such as Ryugu. And so there are some processes to erase such a kind of small craters. So that means the surface of the asteroid Ryugu is very active, not so quiet, active world. Okay. So this is a summary of the SCI impact experiment. The scientific results. Crater was formed in the gravity control regime. That means the gravity determines the crater size. And that means the very weak subsurface layer and small natural craters on Ryugu can be formed, but easily erased. And a pit was formed. Yeah, looking at carefully the crater, from the crater, we can see a cavity inside the cavity, inside at the center of the crater. This is called a pit, and this suggests that there is a double layer subsurface, weak on the strong layer. And the crater scaling law was obtained for Ryugu. The scaling law is the equation to predict the cratering, for example, crater size or something. And this suggests that the surface age is about 8 million years, very young compared to the solar system history. Okay, and particle size of the surface areas are also can be estimated by analyzing the ejecta current. And the subsurface areas particles are small compared to the top layer, but not so small. Okay. And this is a crater viewed from an altitude of 5 kilometers. Can you find the craters? Yeah, it is very difficult. And actually here, yeah, it is very difficult at an altitude of 5 kilometers. Yeah, but looking carefully, you can see that the darkened area, and this may be caused by the ejected deposit. So after the SCI operation successful SCI operation, we went to the second touchdown because we want to collect subsurface materials. And comparison between samples from different points and different depths, it is very, very, yes, helpful to understand, to review the Ryugu's history and what is the, to answer the question, what is the asteroid? And we need to check the possibility very carefully because but we need to check the possibility of that touchdown very carefully because we already have a treasure in the first touchdown. So we carefully check, and finally we decided to go to the second touchdown, and the second touchdown was succeeded on 11th July 2019. Yeah, this was also a very difficult task, but same as the first touchdown, we get the samples from the point where the ejecta material deposited. That means we will get the interior materials by this second touchdown. Now, after touchdown 2, there are some missions are conducted, and then say goodbye to the asteroid. Then Hayabusa2 going back to the Earth, and samples will return to this Australia desert, Umera desert in Australia. And the capsule re-entry was conducted on December 6, 2020. Yes, like this. And this is a movie re-entering the capsule, re-entering the atmosphere. I was not in the desert, but I watching this movie alive on live cast. So I was very motivated. Yes, I was very happy to see this movie. And finally, the capsule was found and recovered, and then now it turned out that we have Ryugu samples of 5.4 grams. This is very, very large amount because at least we were happy if we have only 0.1 gram. So about 50 times as much as 50 times we get samples. And so there are lots of big pebbles and rocks, and now these samples are analyzed, and there are lots of things revealed for the history of the Ryugu. And Hayabusa2 itself left Earth for the extended mission. Capsule is went back to the Earth, but the Hayabusa2 itself once again going left to the space, and a long journey to an asteroid, 1998 KY26, and this is a very small. The diameter will be 30 meters or so, very small. But this is the fast rotating C-type asteroid. Fast. This is a rapid rotating C-type asteroid. Yeah, it is a very important asteroid type. So now Hayabusa2 is going to the this asteroid. Okay. So Hayabusa2 mission completed. Ryugu was found to be an incredible asteroid, and 2 touchdowns and sampling were succeeded. And for me, it is very important. Artificial crater was successfully formed, and large amount of samples were recovered. So this is a summary of this talk. Yeah, impact exploration is an effective means of exploring the interior of an asteroid and a great opportunity to pursue the science of impact on real celestial bodies. So impact exploration is very effective means. Okay, and Hayabusa2 impact experiment was successful, forming an artificial crater with a diameter of a very big diameter of more than 14 meters, and imaging the crater formation and ejection processes from the start to the end, and probably getting interior materials of Ryugu. So we can construct a model of cratering on asteroids, and we can estimate the subsurface area of Ryugu. So what's next? Now, yeah, impact exploration with a SCI or some other impactor is being planned so many times, and so yeah, I hope I hope you will look at another impact exploration in the near future. So that's it. Thank you so much. Anyone, any questions? Okay.
Yeah, thank you, Koji. So, anybody has any doubts? Yeah.
Hello, sir. I had one question. How is the element for the projectile? How is that chosen? Like for the first one, it was something else, and the second one it was copper. How is that chosen?
Yeah. The impact projectile. Okay. The projectile for the sampling is made of tantalum, and the projectile of the SCI is pure copper.
Okay.
Yes, and these are chosen by there is a reason. Yeah, and because the tantalum and copper, pure copper, is very rare or almost doesn't exist on the surface of the asteroid. Right. So if the fragment of the projectile is mixed and collected, we collect it, so we can identify and we can distinguish this is a asteroid material and this is just a fragment of the project. So that's why we choose tantalum and pure copper. Okay.
Thank you.
Yeah.
I'm not a researcher of this field, but I have some simple question that near Earth asteroids, are they part of the main asteroids belt? What is the present understanding?
Present?
The near Earth asteroids, are they part of the main asteroid belt, which is between Mars and Jupiter? So is it so, or what is the present understanding? I mean, the near Earth asteroids are actually part of the main asteroid belts or not, or were they formed in a different epoch, a different way? I mean, what is the present understanding? I mean,
okay, yeah, the present understanding of the near Earth asteroid is that the nearest asteroid also originated from the main asteroid belt, and in the older time, the effect of gravity effect of the Sun, Jupiter, and Mars, or some other asteroid around, some of the asteroids going down to the Sun, and yes, so yeah.
So do you expect some different characteristics of those asteroids which are coming towards the Sun? Will they be in heavier or more metallic? I mean, any kind of possibilities do you predict? Or
Okay. So there is yeah, difference between the nearest asteroid and Jupiter in the content or the type of the asteroid. And in the nearest asteroid, almost nearest asteroid consists of the stony type asteroid and the C-type asteroid, including the carbonaceous something, or very primitive asteroid is very rare. But in the asteroid belt, there are a lot of stony asteroids, but also the C-type asteroid is also distributed relatively these regions far away from the Sun. So that means the born in the asteroid belt, but some of the asteroid belt asteroids going to the Sun with by the gravity effect, and now it near Earth exists. That's why the stony asteroids are almost any year stony asteroid, and the C-type asteroid is rare. Okay.
Okay, thank you.
I think so.
Hello, sir. Thank you for the talk.
Thank you.
I just wanted to ask about that darker patch after the impact. So, you said that it's ejecta material. So, is there any relevance with the mineral composition, difference in mineral composition of the surface or subsurface?
Okay. Actually, this is the problem is not resolved. Why the ejecta deposit is darker than the unknown surface, and maybe the contents of the itself are different. For example, the interior materials are rich in the darker materials such as the
Iron,
yes,
FEMG, yes.
yes, yeah, carbonaceous materials, or the under surface ground materials could be the very small size particles, and the darker and brighter could be from the difference of the particle size. And there are some hypotheses, but it's not clear. So that is the issue to be resolved in the near future. Okay.
Okay. Thank you, sir.
Thanks for this nice talk. I just wondering that how much time, like after the discharge, then the whole system came back to the safe position, and the camera also separated from the from Hayabusa, right? So what is the time gap in between this?
you you want to understand the operation sequence,
Yeah,
right?
I just
Okay. Yeah. Now SCI was separated here, and it it flows here around 40 minutes.
40 minutes.
40 minutes. Yeah,
Okay.
waiting because the yeah SCI Hayabusa2 itself should evacuate to this safety zone. So the only 40 minutes are
Oh, okay.
left for the
Within 40 minutes, everything happened.
yes.
Okay. It's very
Yeah.
challenging and nice. Okay. Yeah. Thank you.
It's very dangerous operation. Yeah, crazy operation in the space mission. Yeah.
Any online audiences, if they want to ask any questions? Parth, you can unmute yourself and ask.
Thank you, sir. So in one of your slides, you estimated age as 8 million years, something like that. You estimated the age. So how did you went about estimating age based on an impact experiment and without having sample in hand?
Okay. To estimate the surface age, it's a long story should be talked, but yeah, we count the surface age by counting the craters on the surface, number of the craters on the surface, and lots of craters exist. That means the surface is very old, and small craters, small number of craters exist. That means the surface is very fresh, because on the asteroid surface, even in the lunar surface, meteorites or small bodies hit the surface so many times. So the larger, the older the surface, the larger number of the craters formed. And this is a very qualitative interpretation. And if you want to quantitative interpretation of the surface age, we should know what size of the crater was formed. Is formed by the impact of the asteroid, meteorite. So that means the crater scaling law was needed to estimate the crater size. To estimate the crater size to the flying gold meteorite, right? So anyway, to exactly construct the model of the cratering process and the crater equation to predict the crater size, that we can understand that we can estimate more exactly the surface age.
So it must have been a challenge with Ryugu, because, as you said, the small craters are vanishing.
Yes.
So that you have must had a big amount of error in that, like plus minus some years. Okay.
Thank you.
Thank you. Any other online audience, or if someone wants to ask, you can unmute yourself if there are any other questions. Okay, so if there are no more questions. Are there any questions? No? Okay. So, on behalf of Manipal Center for Natural Sciences, MAHE, I express my gratitude to our speaker, Dr. Kujiwada, for accepting our invitation and delivering an extremely good talk. I would also like to thank our audiences, online as well as offline, for attending and making this session interactive. I especially thank our former director, MCNS Dr. M. Prithviraj, for approving this series, without which none of this would have been possible. I thank our teaching staff, MCNS, for the constant support. And I also thank the non-teaching staff of MCNS for the arrangement and for making the hybrid session work effortlessly. Finally, I thank all the organizing committee members. Thank you, sir, and thank you all.
Thank you so much.